Alright, so for this problem, we want to find the displacement at point C, which is actually the midpoint. We have values for the moment of inertia, and we have values for E. And we're going to use virtual work for this problem. So what is, or I should say, what are the sections of the beam that we need to do to write the real moment? So if this is the real force system, we're going to have to write a real moment that exists between A and B, and then a different equation that exists between B and C. Okay? And then we'll handle the virtual system later. So let's do that first. So let me find the reactions to this problem. So I'll have my AY reaction and DY. And let's find those reactions. So I'll assume right-hand rule for my sign convention, and I'll sum moments at A. Make sure they're in equilibrium. So summing moments at A, I should be able to find my DY reaction. So the 16 kip force creates what kind of moment about A using this sign convention? Right, negative. So I've got 16 kips times a moment arm of 10 feet. And then way over here, dy creates positive moment with a moment arm of 40. So what is dy?
4.
That seems reasonable. 4 kips. And then assuming up is positive, I'll sum forces in the y direction. Make sure they're in equilibrium. And in that case, I assumed AY was acting up, DY was also acting up, and then I have my 16 kip force acting down. So it looks like AY will be 12. So I have my reactions. So let's now start with the real system. And let's write equations for moment in that system. So as I mentioned earlier, we're going to have to write an equation that's good from 0 to 10, and then a second set that's good from 10 to 40. So let's start with the first one for x equals 0 to 10. So let's draw a free body diagram for that section. I have my AY force, which is 12 kips. I'm cutting that at some distance x, and I'm looking at the internal moment at n. Well, that's not too hard to do, is it? So if I sum moments about the cut that I just made and make sure it's in equilibrium, equal to 0, what do I get? I have my internal moment m. Then I have a negative moment created by the 12 kip force times the distance of x. So it looks like my moment in this section is just 12x. And that'll have units of kip feet. Now the only thing I can check with now is that the moment at A, which is x equals 0, should be 0. And you see my equation does give me a moment of 0 when x is equal to 0. So that's all I can do right now. Now let's cut it somewhere here between B and D. And when you do that, I think working the right-hand side is going to be to our advantage. So this will be an equation that's good between x equal 10 to 40. Let me underline those so you can see that. So I'm going to, at some distance x, I will have, oops, getting kind of wobbly there, my free body. On that side, dy is equal to 4. I'll still have my internal moment, which I'll draw again in the positive direction. And I have momentarily left out the length of that segment. So it's x to the cut, so this should be 40 minus x. So again, if I sum moments now using right-hand rule as my positive sign convention and set everything equal to 0 for equilibrium, excuse me, I have a minus m, negative moment, and then a positive moment created by the 4 kips times a moment arm of 40 minus x. So it looks like my moment here will be, I'll just run the 4 through, so it looks like I get 160 minus 4x, and that will have, all the terms will have the units of kip feet. Now this equation I can check, because in this section from 10 to 40, I know at x equal 40 the moment is 0, and you put x equal 40 here and you get 0. That's good. Now these two equations...
60 plus 4x.
Sorry?
You have a minus m in the above the equation.
Yeah, I just moved that to the other side of the equation.
Oh, okay.
So it should have left me positive 60 minus 4x. Well, we can check. Now the next thing I was going to ask you to look at is they do share a point at B, which is at x equal 10. So when I put in x equal 10 here, I get 120. And when I put x equal 10 here, I get 120. So it seems like the equations match. So I like those. So the next thing I should do is my virtual system. Now to do that, I have to redraw my beam, which I will. And now the question asks for the displacement at C, which is right in the middle. So there's my virtual load, right in the middle, at 20 feet and 20 feet. I won't go through the statics to show this, but I think you guys could probably quickly find out that that'll give you a result of 1/2 and 1/2. And now I'm going to repeat the process. I want to find the moment in this beam. So I'm going to have different limits. So I'm going to have a virtual moment that's going to be good for the first 20 feet, and then a second one that's good from 20 to 40. So in this case, I'm going to be looking at a range from 0 to 20 for the first one. So I cut the structure here. I think the left side will be easier to deal with. So I'll draw that. So I'm going to cut a distance x. The reaction on the left-hand side is 1/2. And of course the moment at the cut, this is a virtual moment, so I'm going to use the lowercase value m. And if you sum moments at this cut with right-hand rule as your sign convention and set it equal to equilibrium, you'll have positive m minus 1/2 times x, so the virtual moment is just x over 2. And you can check that. At x equals 0, the moment should be 0, and this equation gives that. I didn't leave myself much room to do the second cut, so I'll have to do it down here. So I'll say now from 20 to 40. I didn't draw this in before, but let me I'll help you visualize it. That would be this cut. So I want to look at I think the right-hand side would be easier. And the reaction on the right-hand side is 1/2. And that cut is occurring at some distance x from the left, which gives us a little length of our segment of 40 minus x. And we have our internal virtual moment. So let's make sure that's in equilibrium. So again, I'll sum moments using right-hand rule. That's my sign convention. And make sure everything's in equilibrium. So doing that, that moment would be negative with my sign convention. The 1/2 would be a positive moment with a moment arm of 40 minus x. So it looks like the virtual moment is, I guess I could run that through. It's going to be 20 minus x over 2. And again, this moment is strange. It's just going to have the units of feet. Because remember, the force is dimensionless. Now we can check this. In this segment to the right, we know the moment at D is 0, and that would be at x equal 40. And you put x equal 40 here, you do get 0. And then do these two equations give the same moment at the place they share, which is at x equal 20? When you put 20 in here, you get 10, and when you put 20 in here, you get 10. So it looks like all these moment equations are valid. So what I need to do next is write my virtual equation. So let me slide this up here around the paper. So what I now can do is say the displacement at C is the integral from 0 to L of my real moment, my virtual moment, divided by EI over the length. Now, when I look at my real moment, I have an equation that goes from 0 to 10, and I have a virtual equation that also covers that same space. So I'm going to have to break it up from 0 to 10. Now, when I go from 10 to 40, I can use the same real equation, but my virtual equation is good only to 20. You see that? Yep. So now I've got to break that up from 10 to 20. Now I've got another real equation that's good all the way from 20 to 40, and that matches this one that's also from 20 to 40. So the final piece would be this. So you can see why on the exam at this point it could be a rather tedious process to run this all the way out. So I'm just going to go ahead and fill in the blanks and then we'll stop. Just to save some time, I'm going to factor out that 1 over EI. So I'll have the integral from 0 to 10 of my real moment is 12x, and my virtual moment is x over 2. And then from 10 to 20, well, I have to switch to this real moment, which is 160 minus x, 4x. But I'm still using this part of the virtual moment. And then the last component, from 20 to 40, I'm still using this for my real moment, but now my virtual moment equation shifts to 20 minus x over 2. So there would be my virtual work equation. I think I'll stop here, but normally what you do is go ahead and do this integration, evaluate it, get your numerical value, and then divide by E and I. I may actually finish this for homework, and I'll post the final solution, but I'll stop here for the video. Any other questions? This is probably where I'd ask you to stop for the exam. Any other questions before we stop? Okay.